So this is the D flip-flop. So let me just give you, uh, you have seen the basic structure of a sequential machine. So a sequential machine has a present state, or rather, maybe I can just look at one of those examples here. So this is a typical structure of a sequential machine where you have a present state, okay, and well, this is really, so depending on your input, you make a transition, all right. So this is, you're making a transition to this on 0, and you're making a transition to this on 1, all right. And uh, you have some output, okay. So you also have some output. So based on that you have, so you're already familiar with, in fact this was also explained earlier. So you have a combinational circuit, and then you have delay elements, okay. You have delay elements. So you're applying some inputs here, and you can say that so these are your primary inputs, and these are, so you can call this PI, and these are your primary outputs. You can call this PO, and these are your secondary outputs. Call this SO, and these are your delay elements. So these are your, okay, and this is your combinational circuit. Sometimes you also call it a combinational cloud. All right. So this whole thing is called the Okay. So this is the Huffman model. So here, so we are now just going to examine. So a common realization of this, I mean, you can have many flip-flops. So a common realization is the D flip-flop. And that is what we are going to look at now. So, I mean, you can have many kinds of, we'll be looking at a variety of flip-flops in a later lecture. So for us, for now, let us just focus on this. All right. Okay. Now, so let us just see. So the the main circuit configuration of a flip-flop is here. Okay. So if we just think of this kind of a circuit. So if you just think of this circuit, so this circuit is a well, you could say that these are cross coupled. So this will output is you know so it can store a value, uh, a value, or let me say a 0 or 1 value. Okay. So, I mean, you really don't know what it is going to store, but whatever it has, it just say if it's a 0, it stores a 0. If it is a 1, it stores a 1. Now, this is not particularly helpful because you don't have the option to change what it stores. So, instead of having a cross-coupled inverter like this, instead of having a cross-coupled inverter like this, we instead have something that's a little different. All right. So let's say we have something that's a little different. So instead of a NOT gate, what if you were to put a NAND gate? Okay. So instead of a NOT gate, you can put a NAND gate here. All right. And then you have, let us say, two inputs. We can put the inputs in the same direction. Okay. So you have got two inputs. Now, so let us call this A and let's call this B. All right. And let us call this output Q. So what happens is, suppose, so Q is evidently input as well. So suppose, let's make a table of, all right. And let us look at some. So, I mean, you can just call this as, let us say, Q bar, Q dash. Okay. Let us call this Q dash. I mean, I'm just calling it Q. Let me call it Q prime. I mean, don't mistake this prime for a complement. It's just a new value of Q. So if this is 0 and this is 0, then irrespective of the value of Q, okay, Q prime is 1. Maybe if I move it a bit this side. So and Q bar prime is also 1. All right. Is this okay? You understand this row? So if I set A to 0 and B to 0, then irrespective of the present value of Q or Q bar, the output. So this is not a very useful combination of A and B. Okay. This is not a very useful combination of A and B, because both are both become 1. We would like to have a certain relation between Q bar, Q and Q dash. We want these to be complements of each other, because only when these are complementary do you have this latching. So let us consider another.
Sir,
Yeah.
sir, what is the quantity Q bar prime?
Yeah, this is the next value. So this is, let us say, new. New values, let us say. These are your new values. All right. So 0, 0 is not a very useful input. So pair of inputs for A and B, because it makes, you would prefer, because Q and okay, you can see that in this circuit, if you call this Q and if you call this QR, these are complements, right? So you want them to be complements. What if this you have 1, 1? Then this is, you know, sorry. So this is good. All right. This is good. So that means if you keep A and B to 1, then it retains its old value, right? It retains its old value. Or no need to. So I'll just write old value is retained. So that's useful. You are able to retain its old value. So let us just see, do we have such a situation? So in fact, if this is 0, if you have a 0 over here, if you have a 0 over here, then what is the output? Here you have 1 and here you have 1. So this is akin to this row, right? So if you have a 0 over here, then you have a 1 and you have a 1. So this basically it's just latching, okay? In fact, when this is 1, this is like an inverter. When that is 1, it is like an inverter, okay? When this is 1, so let us say that if this is 1, then this behaves like an inverter. All right. So you know how to latch a value, but you also want to set that value to something, So you would also like to store a 0 or a 1. So let us see if we can store a 0 or a 1. So what if you set A to 0 and B to 1? So let us see what happens if you set A to 0 and B to 1. So the moment you set A to 0, this one goes to 1, and this is 1. All right. So let us say that, you set A to 0 and you have set B to 1. All right. So when you set A to 0, this becomes 1. Okay. This becomes 1. And this one means this becomes 0. Okay. So now you have a way to set this to, so the new value, so irrespective of the old value of Q, the new value is 1 and this is 0. And you can see that these are also complementary. So this is, you can say, if you like to say, store 1. And well, let us choose some other color. So now if you do it the other way around, you put it, 1 and 0. So suppose you put this as 1, and if you put this as 0, so now something's the other thing happens. So this is 0, so this is a 1, and now you have 1 and 1, the output is a 0. So it is the other way around. So you have a 0 and a 1. So now you're able to store 0. So now you see you're able to store a 0, you're able to store a 0, you're able to store a 1, and you can also retain the old value. Okay. So now it's a useful device. All right. It's a useful device. So I mean, this is essentially the same circuit. It is. So these gates, these are called, let me just, is it a different color? So these are called steering gates. So where this goes, so you can steer it to either a 0 or a 1, or you retain. Okay, so you can steer the gate in 3 ways. You can steer it to store a 0, you can steer it to store a 1, or you can steer it to retain its old value. All right. Now, so this is the basic idea of a. So this is also called a latch. It's also called a D-latch. You can latch a value to in this circuit. Now, what you see here is that, I mean, both of these, the black part, these are essentially the same circuits. Yeah, you have essentially the same circuits here. But you have an inverter here. So this is kind of, you can say, a log gate arrangement. So you understand what a log gate is. Are you aware of log gates? Huh? Well, log gates are have you seen log gates? Maybe you can just check whether you can see log gates. Oh. So let us look at the image of a log gate. So if you look at this, you see that there are 2 gates here. Okay, there's a gate at the far end and there is a gate at this end. So so if you have a waterway, so this could be at a higher level and the other side could be at a lower level. All of these.
Maybe Sharem, if you click on one of the image, it will be.
Yeah. I'm just looking for an image which is sideways. I'm just looking for a sideways image. Okay. Anyway, immediately I'm not finding a sideways image. But anyway, so let us look at a simple image here. Yeah, so I think okay, so this is good enough. So you have water. So if a boat has to go by, it can go in either way. So what you do is you close one of the gates and open the other. Okay. So water on one side will be, let us say, at a higher level. I mean, that is when you use a log gate. If the water on both sides are at the same level, you don't need a log gate. So you close one gate and open the other, so the boat can come in, it stays here. Then you close this gate and open the other, then the boat can go out. Otherwise, the water will always pass in one direction, so the boat cannot go in. So this is especially important if the boat has to move opposite to the level of the water. So this one is is similar. This one is similar. So here, what happens is, so the data can't just rush through these two stages. So it can, because of this this log gate arrangement. So when the clock is 1, this part can be set to some value, but so when this is 1, of course, this is 0. So this part remains locked. And then when you set the clock to 0, this part gets locked, and the value that is stored here, this one is pushed into this. Okay. So you don't have data can't just pass through straight. If it passes through straight, if you look at the previous circuit, if it passes through straight, then you can have oscillations. The state of the system will be undefined. I mean, we'll see. So we can have asynchronous systems which are carefully designed so that you don't have undesirable oscillations. So here you don't want data to pass through straight, because if it passes through straight, you can have oscillations. That's why the storage element, it has a log gate arrangement as shown over here, so that the passage of data is controlled, and it is controlled by means of this clock. Okay, so you can say that the passage of data is controlled by the clock. So let us just shift it a bit this side. Is controlled by the clock. Okay, and that's why it is called a synchronous. These are called synchronous sequential systems. All right, because the passage of data is controlled by a clock. Anyway, so this should give you the basic idea of how the sequential circuits work. All right. Yeah.
Sir, where you drew the truth table of D latch, D flip flop, can you go to that written slide? Sir, here how are we deciding that whether the means circuit is storing 1 or storing 0?
Oh, can't you see here? So you just see what happens. You put a 0 for A and a 1 for B. So when you put a 0 for A, this output becomes 1, right? Because you have put a 0. So when any input of a NAND gate is 0, the output goes high, right? Now B is set to 1. So you have a 1 here and a 1 here. So the output is 0. So now it is latching a 1, you can say. I mean, if you consider this as the latched value, so you can say that it is latching a 1, right?
So
And similarly for this. Okay.
the value stored is the value of Q.
Yeah, I mean, yeah, that is the convention. Yeah.
Okay.
All right. So that is how this there's a basic mechanism of working. All right. Now I think in this semester you're also doing a course on this theory of computation, is it? Or whatever you call it. Uh, Automata theory.
Flat.
Flat.
Yes,
Yeah.
sir.
So, so these are intimately related. So what you're seeing here, these are just physical implementations of your finite automata. That's all. These are of course synchronous implementations of your finite automata. So it is the same theory which is applicable here, but we are focusing more on the implementation. Okay. All right. So have you done this example yesterday? All right.
No. This we
No.
did
Okay.
not do. We
Then
did the
let
other
us.
pattern one.
Sorry. Hello.
We did the pattern one. We did not
Oh,
do this.
okay. So let us look at this example. I mean, this is a simple example. So you are already when you studied number systems, you saw how you can complement a number. So how do you complement? So let us just consider a binary number. Let us say 1, 0, 1. Say 0, 1, 1, 1. Okay. So how do you obtain the 2's complement? So first you do a bitwise complement. Okay. Let us just call it bitwise complement. So bitwise complement is 0, 1, 0, 1, 0. Oh, sorry. This is not a good example. Let me just change the example. Say, let us consider an example like this. So you as a 0, 1, 0, 1, 1. All right. And then you increment, right? Then you increment. So when you increment, just say, so this one becomes a 0, this one becomes a 0, and this one becomes a 1. So you can say that let us and so this one becomes a 1, all right, and then this one was this one becomes a 1, and then the carry stops moving forward, right? So and this one remains 0, this one remains is a 1. All right. So what you can see is that the initial run of ones uh, uh, initial run of ones no, here everything is complemented, is it? Oh, yeah, maybe, okay, suppose we had a 1 here. So here you'd have a 0. So this one would become a 1. So, yeah. So what we are having is that the initial run of ones, so suppose you have a, say, 1 0 1 1 1. Let us see what happens here. So this is 0 1 0 0 0, and then you add 1. So here you have, oh, 1. Then now what is happening? This, oh, oh, sorry, this was okay actually. Sorry, I just a bit confused. I think this was okay. Yeah. Yeah. So the initial runoff, yes, sorry. The initial, this pattern remains the same and the rest are complemented. The rest are complemented.
Sir,
Ah,
in
I,
the above example, when we add 1 to 0 1 0 1 1, we get 0
yeah.
double double 0.
Sorry, I made a mistake here. Sorry. This one remains the same. This one remains the same. This remains the same as 0 1. Yeah. So the basically the this run. So you have some pattern like this, followed by 1 and some number of zeros. So that becomes, say, B1, B2, B2, B3, B4. So B1, B2, B3, B4. So these get complemented and these remain the same. All right, these remain the same. So yeah, so that is what we are capturing over here. So what happens is uh, a run of zeros, the initial run of zeros will remain the same. If the first one remains a 1, and then everything gets complemented. So here, what you're having, the initial, so we are starting from the LSB. So the initial run of zeros, so the representation is of this form. So this is a state. So this is the input. This is the representation. So this is your input and this is your output. So you input a 0, you get a 0. So the initial run of zeros remain unchanged. The first one remains unchanged, and then everything gets complemented. All right. Then everything gets complemented. So this is uh, your finite state machine. These are also called finite state transducers. So you might be familiar with the term transducers. Transducer basically takes an input and gives some output. So yeah. So this, I mean, you might have studied earlier that, for example, a microphone. Microphone is a transducer. It takes, you know, sound waves. Sound waves are basically mechanical inputs, and in response to that, it produces some electrical output. So that's a transducer. So here, of course, the input is a bit stream. You have some symbol. So the input is really a symbol from the input alphabet, and the output is a symbol from the output alphabet. So in that sense, it's a transducer. So in response to some input, it produces some output, and that is of course conditioned according to the state in which it is. All right. So this is your this is your logical machine, but and this can also be represented in a tabular form. So the present state may be either Q or Q1. So in case the present state is Q0, as you can see on input 0, the output is 0. And on input 1, the output, well, rather, let us see, on input 0, so here, this of course, so on input 0, the next state is Q0 and the output is 0. On input 1, the next state is Q1 and the output is 1. And okay, so and on if the state is Q1, then on 0, so in case of Q1, the next state is always Q1. So if the input is 0, output is 1. If the input is 1, the output is 0. All right. So this is how it works. All right. And but so this one is just it is a tabular representation of this diagrammatic representation. Now, if you want to implement it, you have to decide on a bit value for Q0 and a bit value for Q1. So these are called encoding. So what you are doing is we are encoding the state. So Q0 and Q1 are symbolic states. But when you want to implement it, you got to encode the symbols with certain values. So since there are only two states, you can distinguish between those two states with a single bit. So you can you could, for example, use 1 for Q0 and 0 for Q1. And if you substitute those values, then you get Boolean functions for the. So you have two functions, as you can see. You have the next state function. And you also have the output function. So this is actually, it's the next state function and this the output function for various inputs, for 0 or 1. All right. So you essentially get two truth tables. One truth table for the next state function, by collecting, this and this, you get the TT for NS, and collecting this and this, you get the truth table for output. All right. So that way you can, construct. So you know how to realize combinational circuits. So essentially, you're able to realize this, this combinational cloud. This is for the next state. And output functions. All right. So once you do that, you're able to realize your combinational circuit. Now, now note that these choices, the choices for encodings do have consequences. And in fact, it will be a good exercise for you to, try this out and see. So, in other words, depending on your encoding, you might have a bigger circuit or a smaller circuit. Okay, so now it is not a very easy matter to decide on which encoding is best. Of course, you could enumerate, but that is expensive. Yeah. All right. So this is your simple. This is a simple Mealy machine. Of course, I think yesterday I've already seen the definition of a Mealy machine. So in a Mealy machine, the output is a function. This output or you can just say depends on the present state and the inputs. And you also know about the Moore machine, where output depends only on the present state. Now, one advantage of the Moore machine, of course, is that it has a stable output. It has a stable output. Because as you have seen, I mean, in the present state, if you keep changing the input, the output will also keep changing. So if you want the output to be stable, this Moore machine is a better choice. But of course, it comes at a cost. It usually has more number of states, okay, of the same behavior. So we'll look at some examples of Moore machine as well. Okay. So,
Sir, suppose we swap the encodings of Q0 and Q1. Then, like even then, the output will remain the same. Then what is the issue?
oh no. output should remain the same. If the output changes, you have a problem, right? So the encoding of the state does not change the behavior of the machine. It just changes the implementation. So it's possible that a certain encoding will lead to a combinational circuit with less number of gates, whereas some other encoding might require a combinational circuit with more number of gates. But the behavior doesn't change. The behavior of the machine remains the same because your behavior is defined by the truth table, right? So, so the truth table, for the encodings. So in fact, here you have yeah. So for this encoding, this is how you get the truth table, right? So wherever there is Q0, I put a 1, and wherever there is a Q1, or have I done it the other way around? So here I've, so here what I see is that I've encoded, yeah, I put 0 for Q0. This is for Q0, I put 0, and for Q1, I put 1. So this is not the same encoding. All right, so I've actually used a different encoding. So wherever there is Q1, you can see that, or have I made a mistake? Oh, I think I made a mistake. This should be 1. What have I done? Let me just check. If the present state is Q0, the next state is Q0, that's all right. Yeah. Oh, I think I made a mistake here. This needs to be corrected. Yeah, sorry. This should be 1, this should be 0. Both should be 1. I think I've mixed up. Yeah, sorry, I'll have to correct this. Yeah. So, yeah, so this one, so wherever I have a Q1, I'll put the encoding of Q1. All right. I think I might have messed up some. But anyway, the outputs also should not have changed. But
Sir, is there any situation where if we change encoding, the output changes?
no, it should not happen. Then you're changing your machine.
Sir, what is the significance of encoding the states? Like,
If you don't encode, how will you realize? This you can't realize, right? This is a symbolic machine. When you realize, you got to realize in terms of bits. I'm sorry, let us look at another. This one seems to have problems. Let's just look at another example. Yeah, okay, so I hope I haven't made the same mistake here. So let us just see whether this is okay. So Q0 is 0, 0, right? So let us just check. So Q0, this is 0, 0, and this is 0, 0. Wherever I have Q0, I should have 0, 0. So that is all right. Then, so this is okay. Let us see Q1. Q1 is 0, 1. Or if you like, I can use a different color. So Q1 is 0, 1. So Q1 is 0, 1. So this is 0, 1. Here I have Q1, so this is 0, 1. And here I have Q1. Yeah, this seems to be all right. I think somehow I made a mistake with that. Q2 is 1, 0, so let's choose a different ink there. So this is 1, 0 for Q2. So this is Q2, this is 1, 0. I've got Q2 here, this is 1, 0. No Q2 here. Oh, sorry, I should have. What about Q1? So Q1 was green, right? So Q1 is 0, 1. Yeah, so this is 0, 1. All right. And let us say Q3. So Q3 is 1, 1. So this is Q3. This is Q2. So Q2, sorry, I missed that. So Q2 was 1, 0. This is 1, 0. That's all right. Then this is Q3, which is 1, 1. And this is 1, 1. So these are all right. Now let us look at the output encodings. So output encodings, well, if you like, let us say this is 0, 1 for A. So where do I have A? This is A, this is 0, 1. So this is your output encoding. 1, 0. So let us see 1, 0. 1, 0, 1, 0 for B. So you have B, which is 1, 0. And well, that's the only place you have a B. And this is C. So C is 0, 0. So let us just take 0, 0 for C. So C. So these are all 0, 0. And I got C here. So yeah, so that's all right. So yeah, this seems to be okay. Yeah, sorry, I got some too many mistakes in that earlier one, so I'll have to correct that. Yeah, so this is all right. So now you see, when you have these encodings, you can construct the present state and the next state functions. So when you so what about the next state function? Let us see how the next state function looks like. So next state function is, say, the present, so 0. Well, if you like, let us say 0, 0, 0, 1, 1, 0, 1, 1. And if I just put that input with, say, blue, all right. So here the input is 0, okay? The input is 0. So what is the output? What is the next state? So these are your inputs, these are your outputs. So output is, as you can see, 0, 0, 1, 0, 0, 1, and 1, 0. And, you know, I can take it further. So this one will be, here the inputs will be 1. And let us say, so here again, these are 0, 0, 0, 1, 1, 0, 1, 1. And the outputs are, I take from there, 0, 1, 1, 1, 0, 1, 1, 1. So you can say that these are, I mean, I'm just using this x1. If you say that these are 3 inputs, x1, x2, x3, and this is y1 and y2. So I've got these 2 output, y1 and y2 correspond to the next state function. And similarly, in similar vein, I can also construct the output function. So the output function, just by gathering this, so here it will be, this output function, let us say Z1 and Z2. So this one will be 0, 0, 0, 0, 0, 0, and 1, 0, and here it is 0, 0, 0, 0, 0, 1, and 0, 0. So this is, this is your, for the encoding, for the given encoding. Which is this? This is for, this encoding. For this encoding, this is your function. So I hope you understand this.
Yes, sir. Yes, sir. Understood.
All right. So that is why you need to encode. Yeah. Unfortunately, there were mistakes that I left to correct that one. Yeah. All right. So this is well. I think I'll not have to explain this machine to you, that you should understand quite easily on your own. There's a machine that recognizes, it's a recognizer for 101 and 110. So whenever I get an input ending with 101, okay, so you can say that this one recognizes beta. So any string of this form, okay, any string of this form, so you can say alpha, beta. So it recognizes strings of this form. All right. So this is the machine. So this one is the symbolic machine. So this sort of machines you actually probably design in your flat course. But if you want to implement it, you'll have to have some encoding for the symbolic values, and then you get functions which you can implement using gates. All right. Okay. So I think these things you can you can follow these on your own. Okay, I'm not going through these. These are just similar exercises. So I'll leave it to you to do this. And the important part is, of course, here that the output depends only on the present state. All right. Otherwise, yeah. And yeah. So now let us look at. Okay, before we do the conversion, let us take a break for 5 minutes. We can resume, say, at 9:20. All right. Let's take a short break for 5 minutes. Yeah, I think we can resume now. So let us consider the conversion of a Moore machine to a Mealy machine. Okay. So the output, so you can have the same set of inputs, I mean, same set of states. What you do is the output of the state of a Mealy machine. Okay. So suppose so the output in state Q, okay, on receipt of the input symbol A. So what will the Moore machine do when you get an input symbol A? It is going to make a transition from Q on A and go to some other state which is indicated by this state transition function. Okay, it is going to go to this state on receipt of the of receipt of A on when it is in state Q, and then in this state it will have some output, right? It will have some output which is given by lambda Moore. So whatever output you have in this state, that is the same output you'd like to have when you get an A when you're in state Q of the Mealy machine. All right. So that is how you can relate the output function of the Moore machine to the output function of the Mealy machine. Is this okay? Any questions here? Hello? Let me have some response. Are you okay with this or?
Yes, sir.
Shudiksha, are you there, Shudiksha? Shudiksha? Swati, are you there?
Yes, sir.
Yeah, so have you followed this?
Yes, sir.
Okay. So this is all right. Now let us, well, here is an example. So I think this, so this is a simple example. So it's an acceptor for even number of zeros and odd number of ones. Okay, it's an acceptor for even number of zeros. So this acceptance is indicated by the output function. So if you notice, the output function is 1 in the accepting state and 0 in the non-accepting states. All right, so if you see the output 1, you know that it has accepted the string which has been given so far. All right, a string of input symbols which has been given so far. So your input alphabet is 0, 1, and your output alphabet is also 0, 1. All right. So with this, of course, your your input and output encodings are trivial. You can have basically 3 encodings: input encoding, output encoding, and state encoding. and state encoding. Okay, so here you can see the input and output encodings are trivial. But your states are symbolic. Okay, your states are symbolic. In fact, you have got 4 states here. All right, you have got 4 states. So you will need at least 2 bits to encode those 4 states. So we have chosen a certain encoding. Of course, other encodings are possible. So for this encoding, well, this is your state. This is a characterization. This is the next state and output. These are the next state and output functions of your machine. Now, in this case, note that your output function has been shown this way because this is a Moore machine. Your output does not depend on the input, so you can do it this way. All right, and for this encoding, so let us just check that EE is 0, 0. So wherever you have EE, you should have 0, 0. All right. And then if you think of, well, EO is 0, is O. Again, I seem to have a problem. EO I put as, oh, there's a problem here. There's a problem. Anyway, let me see, EO. I seem to, EO and OE, oh, so I have made a mistake here. So this table also needs to be corrected. All right. EO and OE are all same. So this table needs to be corrected as well. Sorry about that. Yeah. So this table is faulty. Output, I mean, this is okay, this is trivial, but there are mistakes here, so I'll have to correct that. Okay. Okay, so there's a Moore machine. There's another Moore machine. Well, yeah, so this is yeah. For this, so you can check this as well. All right. So I'll leave it to you to check this. I'll check it up later. Well, here I think I've been a bit more careful. So yeah, this one seems to be okay. All right. All right. So these are various Moore machines, and these are various Moore machines which you can study yourself, and their associated encodings. So I'm not going into these encodings now, or I'm not delving into these machines. I think you can follow these on your own. All right. So let us look at Mealy to Moore conversion. Okay. So in case of a Mealy machine, you know that, say you're in state Sj. So your in state is J. All right. And you have got, so you can have a number of input transitions. And these, you have, output is OK1, OK2, and so on, and OKJ. So these are various, these of course belong to delta. These are taken from your output alphabet. All right. This belongs to delta. Maybe to avoid confusion, I can do it in a. These belong to delta. All right. So you have a situation like this. So now what you do is you create a number of other states. So you create a number of other states. And so you create copies of this state. So you have SJK1, SJKJ. All right. So these are your various. So this one is mealy, by the way. This one is no, sorry. This is mealy. Yeah, this is mealy, and this is more. This is more. All right. So in this state, your output. So your output will be OK1. In this state, the output will be OK2, so on. And in this state, your output will be OKJ. All right. So you're splitting this state into multiple states, so that so that this output will come to this state. This output will come to this state, and so on. This output will happen from this state. All right. So you are having that. Now you have to yeah. So this is what it means, that there's a copy of Mealy machine state J to give this output in this state. Okay, so that is what we have done. Now so now if you have a transition, so if you have a if you have a transition, say you have a transition, say this is SI and your input is A. Okay, so if you have a transition, so now here also SI will have it can be split up as, say, I'm just saying SI1, SI2, and so on. So each state can be split up, right? Into a number of states. Well, maybe not here. So what you do is on A, it will, so if it is on OK1, all right, so on A, it will come to OK1. Okay, so all the new states corresponding to SI will make a transition on A to OK1. So, all right. So if you have more states, say, SI, something. Something J. Or I don't want to use the term J, so all of these will make a transition. Now if one, so suppose is, say, I'm just calling it P, all right. So on B, if it makes a transition to this, or maybe if I can choose a different ink, say if I choose, say this is P. So on B, if it moves here, then this, let us say P1, P2, and so on. So this on B, it will come, sorry, not here, but let us say here. All right. So this is how you can convert a Mealy machine to a Moore machine, okay? And what about the initial state? So you got to be a little careful about the initial state. So you have, so initials, so in the initial state you haven't received any symbol, okay? You haven't received any input as yet. So for that you have a special input, special output symbol called O epsilon, which is distinct from all all the symbols in this. So sorry, or which is distinct from all the symbols in this. So yeah, so the output symbols of the Moore machine will be, will be the set of output symbols of Mealy machines augmented with OE. All right. And you have a new state. You have a new state. You have a new state created as the initial state of the Moore machine when it hasn't received any inputs. All right. And the successor of, so the successors of this are same as those of any copy of Q0 in the created Moore machine. Okay, so I think this can be explained with an example. So yeah, so we saw this example sometime back for 2's complement, getting the 2's complement starting from the LSB. So now let us just see. Let us just see what is happening. So let us consider Q1. Okay. So Q1 so you have got what are the input transitions to Q1? So you have got 3 input transitions to Q1, okay? You have got 3 input transitions to Q1. But more important is that in the state Q1, you could have an input transition with output 1, and you could have an input, so this is with output 1, and you could also have an input transition with output 0. So we create 2 states, okay? We create 2 states, Q11 and Q10, all right? This is a bit redundant. We don't really need this. It's redundant. I mean. So this only indicates that the output should be 0. So this need not be here. Sorry, Q. What have I done? Q1. What's that? This is a little. I would have thought that the output would be 0. So let us just check. I might have made a mistake. So okay, let us just see. So I have a transition. So because I have 2 outputs, 1 and 0, so I have created 2 states, two states, 2 copies of Q1, one to give an output of 1, another to give an output of 0, all right? Though I have put the outputs wrong, different, so there is a mistake somewhere, but let us just see. So now, so this one should be 1. So this one, so let us see. So, so here in Q1, so I have a transition from Q0 to Q1, okay, on input 1 giving the output 1. So when I get a 1, okay, when I get a 1 from Q0, when I come to Q1, I would like to have an output of 1, right? Because I'm coming from Q0 to Q1 on input 1, giving an output of 1. So when I make a transition from Q0 to the appropriate copy of Q1, I should have the output 1. Okay, so I'm getting input 1. So in this state, the output should be 1. Okay, not 0. The output should be 1. All right. Now, let us also look at this. So I have, so now this, so from Q1, when I get a 1, okay, when I get a 1, sorry, from Q1, when I get a 0, I would like to give the output of 1. When I get a 0, I would like to give an output of 1. All right. So here from Q1, okay. So Q1, if I, oh, sorry, sorry, I think, let me just explain. This one, let me just explain. This one is indicating the output. All right. Sorry. This one is indicating the output. So this one is indicating that when I'm in Q1, I'm giving an output of 1. And when I'm in Q1 0, the output is 0. I think it might be okay. So when I'm in Q1 0, the output is 0. When I'm in Q1 1, the output is 1. Okay. Now let us look at this once again. So here, when I get a 1, as I told you, when I get a 1, I would like to give an output of 1. So here the output is 1. Okay. Now, from so if I get a 0, if I get a 0 when I'm in Q1, when I get a 0 when I'm in Q1, I would like to give an output of 1. So these are the two copies of Q1. When I get a 0, I make a transition to Q11 so that I get the output of 1. Okay. So when I get a 0, I'm making a transition to Q11 to get the output of 1. And when I get a 1, when I'm in Q11, when I get a 1, I want to output 0. So when I'm in any copy of Q1, when I'm in any copy of Q1, I want to make a transition to Q10 so that I get the output of 0. So this is a copy of Q. There is Q11. So on 1, I'm making a transition to this to get the output of 0. And from this also, I'm making a transition back to this to get an output of 0. All right. Now, in this case, initially, well, just a minute, please.
Sir, you're muted.
Yeah, it seems I was muted. How long was I muted? Hello?
Maybe for 2-3 minutes you are muted.
No, then I don't know whether.
So no, the previous slide, this slide, the previous slide you go. Yeah. Now here you can start from.
Yeah, but I don't know how long I was muted. Anyway, then you'll have to.
CRM not very long, just 2-3 minutes.
I
what you
think
said.
yeah, this is a bit problematic because I can't keep repeating everything. Anyway, I'll continue with the next slide. So if you look at this machine, you'll find, let us see, we have in state Q1, okay. So incoming, let us look at incoming transitions to state Q1. So this one is an incoming transition. So of course, all the arrows that are pointing, and let us see what outputs we have for the incoming transitions. So this is an output for the incoming transition. This is an output for this incoming transition. This is an output. This is also, no, sorry. This is the incoming transition. All right. So maybe you can, if I use a different color. So I've got two, you can say, output symbols for transitions coming into Q1. All right. So one is 0, 1 and one is 1, 1. So I've got two copies of Q1 where the output is either 0, 1 or the output is 1, 1. All right, where the output is 1, 1. So these are two copies of Q1. All right. Now let us see Q0. So Q0, I've got, so the incoming transitions, I've got 1, 0, 1, 0. This is 1, 0. And there's a different one, which is 0, 0. So accordingly, I've got two copies of Q1 where I have, these outputs, one for 1, 0, another for 0, 0. So now what I'm doing is, let us say for, say, Q1. So Q1 for the input 1, 1. So the input 1, 1. So when do I have the output? When do I have the output 1, 1? I get the output 1, 1 for this input, for input 1, 1. So whenever I have 1, 1, I'm going to make a transition to this copy of Q1 so that I get the output 1, 1. So you see, whenever I have, from Q1, that is from Q1. So from Q1, I come to, I have the output of 1, 1 only on the input 1, 1. So from all copies of Q1 on input 1, 1, I'll come to this copy of Q1 where the output is 1, 1. So as you can see, on these two inputs, or maybe I'll just use this one. So for these two inputs, I'm coming to this state, okay? I'm coming to this state to get the output 1, 1. Similarly, well, look at this. On input 0, 0, also from Q0. So I get, no, sorry, this is, Again, I'm making that mistake. This one is going back to Q0. So let us see, 0, 1. So 0, 1, I can get the output 0, 1 for transitions from Q1, also from Q0. So first let us take, so for all copies of Q0 on 1, 0, 0, 1, okay, 1, 0 and 0, 1, I shall make a transition to the copy of Q1 where I get the output 0, 1. So 1, 0 or 0, 1. So you can see from one second, 1, 0 or 0, 1. I think the detection of the transition may be, no, it's all right. This is associated with this arrow. Yeah, so 1, 1, 0 or 0, 1, I'm making a transition from here to here, okay, to get the output 0, 1. All right, so this output I'm getting, and yeah, and this output I'm also getting when I make a transition from Q0 to Q1. So from all copies of Q0, I'm going to make a transition to this copy of Q1 where I get the output 0, 1. So on 1, 1, okay, on 1, 1 from Q0. So 1, 1 on Q0, all copies of Q0 on 1, 1, I make a transition to this. All copies of Q0 on 1, 1, I make a transition on this. So, so I've explained how I handle the transitions to get the appropriate outputs from Q1. So similar principle applies from here in Q0. Now I look at the initial state. So now initial state, what I'm doing is I'm just looking at all the successors of Q0, okay? All the successors of Q0. Oh, sorry, I have not yet drawn that. So, oh, sorry, this is the initial state. Okay. Yeah, sorry, this is the initial state. Yeah, so actually, this one was, I shouldn't have circled this at this time, but if you look at all the successors of Q0, so the successors of this initial state will have the same successors that are there for the copies of Q0 to get the same outputs, okay, to get the same outputs. So for example, on 1, 1, on 1, 1, I'm going to Q1. So here also on 1, 1, I'm going to this copy of Q1 to get output 0, 1. So same thing. So here I have a successor. So so this is a successor of Q0 on 1, 0, on 1, 0 to get the output 1, 0. So on 1, 0, well, it is both for 1, 0 and 0, 1. So for 1, 0 and 0, 1, I am for 1, 0 and 0, 1, I am going to this copy of Q0 to get the output 1, 0. Okay, to get the output 1, 0. Okay, so and similarly to get the output 0, 0, I'll again have to make a transition to the copy of Q0 where I get the output 0, 0, and that will be on the input 0, 0. Okay, so on the input 0, 0, I make a transition to this copy. All right, so that is.
I think we should stop today.
Yeah, so that is how we handle the conversion of a Mealy machine to a Moore machine, and we have also seen the conversion of a Moore machine to a milli machine. So we can stop here today.
I
Okay.
have one question, students. We need to take another theory test. So when should we take it? Need to take another theory test on the topics after the first test. So is next week okay? Okay, maybe we'll announce it.
Sir,
Yeah.
sir, regarding tomorrow's class, will that be in a hybrid mode?
No, tomorrow we'll take online. We'll take tomorrow. We have not yet got the classroom, so we'll take on online mode only.
The classrooms we have, but I think
No, their projectors are not ready. CRM, they
okay,
are
I'll go
not
and
ready
check
for
up.
hybrid.
I'll have to go and check up. So unless the class is ready, yeah. So I'll have to go and check up.
Tomorrow, let us have online.
Yeah, we'll have it online.
By next time, we'll get it. Next week, we'll get it ready.
All right.
Sir, what is the date of the next test?
Yeah, we are asking you. You suggested it.
Okay.
Sir, what will be the duration of that test, sir? Like
Everything
1 hour, 2 hour?
Yeah, everything will be announced. Yeah.
No, it is like the last test only. So it will be exactly.
Anyway,
the last.
no, the test can be in hybrid mode, isn't it?
No.
If the class is in hybrid mode, test can also be like that.
CRM,
Huh?
all the students are not in campus.
No, that's why it is in hybrid mode. Okay, we'll check on
discuss.
that. We'll see on that.
I think test cannot be in hybrid mode. It has to be either offline or online. Fully offline or fully offline. Test cannot be in hybrid mode.
No. There was a circular on that. We'll discuss it later.
Okay. All right.
No, sir. Sir, I'm asking because the institute has mandated the students to come, so we can plan our travels accordingly so that it does not clash with test dates. Because we cannot come very late also. If
So can
the
you
institute...
do one thing? Can you see? Next test will probably take. We will, or maybe tomorrow we'll tell it. We will internally talk to our authorities. Tomorrow we'll tell.
Yes, sir. Please tell us by tomorrow.
We'll tell you by tomorrow.
Okay. Thank you, sir.
Okay. Fine.